We're going to look at friction today specifically. We'll get to inclines next class. So I told you we'd kind of just scratch the surface on forces. Now we're going to dive into the next two big sections in determining forces. So we're going to look first at two different types of friction. The first of which is kinetic friction. And what does the word kinetic usually mean? Or kina? Motion, right? That prefix or the root there, kina, means motion. So when we're looking at kinetic friction, we're looking at an object that's already in motion. Okay, so friction that acts opposing the direction of an object's velocity. That means kinetic friction can only be acting if an object is in motion. Okay, so remember, kina is motion. When we start to look at the kinetic friction and we start to look at the amount of friction that's being applied, it depends on the two surfaces that are interacting, okay, that are touching. If we're sliding an ice cube on ice, do we think we have very much kinetic friction? No, probably not. But if we're sliding sandpaper on carpet, very much friction? Yes. Okay, so it depends on those two surfaces. Okay, based on a lot of math that I'm not going to go into right now, the kinetic friction or the amount of kinetic friction is found to be proportional to the normal force. Okay, which means, by proportional, I mean directly related. Okay, so that means if we have an increase in normal force, then we have an increase in kinetic friction. So the way I want you to look at this, and here is our equation now. Frictional force equals, I'll write it a little bit bigger here. Yeah, it's a Greek letter. I can't remember what the Greek letter is. Lambda? No. No, it's not lambda. Lambda's the Y. I don't know what this is. I can't remember. Okay, but it's frictional force is equal to, this is called the coefficient of friction, okay? And the K here probably stands for what? Kinetic. The coefficient of kinetic friction. Okay, so in case you couldn't see that up there. Coefficient of kinetic friction. And there's two different types of friction. So we looked at kinetic, which is friction of an object in motion. Now we're going to look at a second type of friction called static friction. What do you think static friction might be? Not moving, right? If something is static, if it's stagnant, right, that means it's sitting still. So static friction is the frictional force of an object when it's at rest, okay, or just before it goes into motion. Okay, so you kind of think of it like this. The static friction is kind of what's holding it in place. Okay, you have to overcome static friction in order to start your motion. Okay, if you're pushing something or pulling something, whatever, you have to overcome static friction in order to begin your motion. Okay, so here's another equation for frictional force, and I'm going to rewrite it. This is what your book gives you. I like to just keep it as a frictional force. The reason they put this max subscript is because that's the maximum frictional force if something is at rest, right? Static friction is the maximum amount of friction that something could have because it's keeping it in place. So I'm never going to write F max. I just want you to see that's what your book says. So I'm still going to write the frictional force is equal to the coefficient of static friction times the normal force. Okay, and you'll rarely even see me write these subscripts. We'll be able to tell what subscript we should be using or what coefficient we should be using based on the problem. So you'll hardly ever see me write those subscripts either. Okay, but understand this is the coefficient. Coefficients are dependent upon the material or dependent upon the object. Okay, so you'll kind of look at a difference here in these coefficients. So I need you to open your book right now, and I want you to read the last paragraph on page 96. Coefficient of static friction or coefficient of kinetic friction, which would you assume is higher? Is a greater coefficient? Static friction. Good, right? A greater coefficient of static friction would give you a greater frictional force. So that's correct. All right, and if you look on page 97, it has a chart with values. So go ahead and look at 97. This is a very, very small sample size of these coefficients. There's a lot more coefficients that have been determined, okay, based on other surfaces and other objects, okay? So if you look at these coefficients of friction, the coefficient of static friction is greater than the coefficient of kinetic friction in every case. Okay. All right, let's try this one. So when we're looking at friction problems, it takes quite a few steps to get to our final answer. For these first couple, I'm going to show you exactly, step by step, kind of how we should get to our final answer here, okay? Our overall goal is to find the horizontal acceleration, but we have to find several things first in order to get there, okay? So that's why there's so many questions. So remember here, our overall goal is to solve for the acceleration. That's the overall goal here, is to solve for the acceleration of our sled. So first thing that we need to do is make sure that we're drawing a free body diagram. Do we think our applied force and our frictional force are going to be equal to each other or not? No. Right, because we're going to have some acceleration. So that means we can't have a applied force and frictional force equal to each other. Okay. All right. Overall, our goal here is to find the acceleration. So we know our applied force is 75. We don't know our frictional force yet. But we need to be able to solve for the acceleration. So let's set up our net force equation first. F net equals F applied minus frictional force. And why am I using the horizontal net force equation here? Yeah, it's moving horizontally. I'm not looking for the vertical acceleration. I'm looking for the horizontal acceleration. Yeah, our sled's not hopefully like flying off of something, okay? So now let's see kind of what substitutions can we do here. Can we substitute something for F net? Mass times acceleration equals F applied, which we know is 75. My frictional force, what substitution can I make for that?
Normal force times 0.01.
Right, the coefficient, which I'm just going to plug in right now as the variable, but yes, you're right, we will put numbers in there. The coefficient times the normal force. And you're right, Claire, we know the coefficient is 0.01. So let's go ahead and do a couple more substitutions. My mass is 50. Applied force is 75. Coefficient is here. My normal force. So now I still have two variables, which will not work. So I'm solving for acceleration. Is there a way I can find the normal force here? Yeah. How can I find the normal force?
Equal to the gravity.
Good. It's equal to the gravitational force. How do we know that?
Because it's not moving.
It's not accelerating vertically, right? So if we know that in the y direction, F net's equal to normal minus gravitational, and this is 0, we know that Fg is equal to Fn. Okay, are we seeing that process? You don't need to write out these steps every single time, but if you're not understanding where it's coming from, that's going to get you there. Okay? So now to find normal force, we're going to take mass times gravity, so 50 times 9.8 equals the normal force, because it's equal to the force due to gravity, which means our normal force is equal to 490. So now I can plug that into my equation right here. Okay, so I'm going to take 50 times A equals 75 minus 0.010 times 490. Which is 75 minus 4.9, I believe. So I'll subtract this side of my equation right here. And then I divide by 50. Sometimes I see people divide by the wrong side. Okay, you got to get the variable by itself. So we have to divide by 50. Divide by 50. And what does our acceleration come out to? 0.52. Wait. Crates pulled horizontally with a force of 710. Coefficient is 0.2. Calculate the acceleration. Can you do this one on your own? Yes. Okay, I think that you can. Let's try it on your own. My bad. (1.2 meters per second squared). Okay, very good.
Despite. I love that. That means our applied is going to be greater than our.
Okay, so we've got a box on a wooden floor. Our free body diagram. We've got gravity. We've got the normal force. Are gravity and the normal force going to be equal this time?
No.
No. Because we've got an applied y. Okay, so we might say that normal force is a little bit shorter. Now we've got an applied force, which is 100 newtons at 40 degrees. Okay, we've also got a frictional force because we were given a coefficient here. And we're working on friction problems. Okay. So this one's going to take a little bit more work because our normal force is not just as simple as making it equal to the gravitational force. Okay? It's not that much more difficult, but it takes a little extra step. Okay? So we want to find overall, again, the acceleration of our box. Okay, I know that's not listed here in our problem, but it takes you through every question again, and I want to have all that up on the screen. Okay, so our overall goal here is to find the acceleration of the box. So let's start by solving for f applied x and f applied y. Okay, will we need both of those values? Why not? We're not trying to find vertical acceleration, but we will need f applied y in order to solve for the normal force. Okay, because it's not accelerating in the vertical direction, we know that upward forces, which there's two of, have to equal the downward force. So we will need both of those components. Okay, so let's solve for f applied x and f applied y right now. It's never going to hurt you to solve for both of them. You might not end up having to use both of them, but it's not going to hurt. All right, what did we get for F applied X? Say it one more time. Yeah, okay. And what about for the other one? Good. 64.3. All right, very good. Now let's go ahead and start looking at our F net equation here for the X direction. Okay, once we break down that 100, remember we're not using that again. We're only using the X component. Okay, so that's why I'm plugging in only F applied X. So we can do some substitutions here. MA equals 64.3 minus the frictional force. My bad. 76.6 minus the coefficient times the normal force. Okay. You can do these problems in multiple orders, right? It doesn't have to be just this particular order that I'm showing you. It does not matter, okay? I'm just kind of walking you through every step. You can do it lots of different ways. There's multiple paths to get to the final answer, and that's okay. All right, so my mass is 30 kilograms. I'm just going to substitute that in right here. And my coefficient is 0.3. So we have acceleration and we still have the normal force. We have the ability now to solve for the normal force. So let's do that. I'll do that in a different color so we don't get mixed up here. So if I want to solve for the normal force, I'm going to look at my F net in the y direction. And how many vertical forces do I have? 3. 1, 2, 3. So it's F normal minus F applied y. I'm sorry, plus F applied y, my bad. Minus FG. So what do we know about the acceleration in the vertical direction? Is the box accelerating in the vertical direction? No, which means this is still 0. Fn plus F applied y, which we know is 64.3, minus mass times 9.8. $229.7, yeah? So we move that to the other side and we get our normal force equal to 229.7. Do we agree with that? So that's going to be plugged in into our normal force, 229.7. So let's go ahead and solve and finish that problem out. Our acceleration I got equal to about 0.256. Okay, so let's try this one. We're going to look at one more, and this time it gives us the acceleration, so we're going to solve for the coefficient. Okay, gives us the acceleration, we're going to solve for the coefficient of friction. So So with these friction problems, acceleration isn't always going to be your only goal. You might have to solve for other things. This time it doesn't tell us what's being applied at an angle. So that means it's just going to be a horizontal force. Okay, so I set up my net force equation in the horizontal direction. This time I know my acceleration, so I'm going to substitute mass times acceleration equals applied force, which I know is 320, minus the frictional force. And you can go about this a couple ways. I'm going to go ahead and solve for the frictional force as a whole, and then I'll go ahead and break it down. You could do a substitution now if you wanted. That's completely up to you algebraically how you want to do that. I'm just going to solve for frictional force as a whole, and then I'll set that equal to coefficient times the normal force. Does that make sense? Okay. So let's go ahead and try this math here. 90 times 1.2 minus 320 gives us what value? Okay, so if I take 90 times 1.2, I get 108 equals 320 minus the frictional force. I'm going to subtract that to the other side, and I get negative 212 equals negative frictional force. Okay, so I can cancel my negatives, and that means my frictional force is equal to 212 newtons. We on the same page right there so far? So now, if I know my frictional force is equal to 212, I can substitute coefficient times the normal force equals 212 newtons. I'm solving for the coefficient. Now I need to solve for normal force. Okay, what do we know about the normal force in this case? What's it equal to? It's equal to the gravitational force. Okay, and that's because we're not applying any more vertical forces. There's nothing else in that region, right? It's not accelerating in the vertical direction. So we know Fn is equal to the gravitational force, 90 times 9.8. So what should I be dividing by in this case? Divide by 882. And my coefficient should come out to be 0.240. The coefficient has no units. Coefficient has no units. Okay? Coefficients have no units. Coefficients are also usually between 0 and 1. If you get a coefficient of like 16, no good. Okay? Coefficients are usually always between 0 and 1. Very rarely you might see them up to like the 5 range, but usually between 0 and 1. Okay, so if you get a coefficient that is out of this world, you need to go back and reevaluate a little bit. Okay, because it's usually, most times I really try to make them between 0 and 1 because that's most realistic.